Okay, then let's start. So let's first quickly recap what we learned in the last class. So far, we are talking about file system interfaces, or what kind of interface and functionalities should a file system um, should give us, or us means the users. So if you're a developer writing a file system, you should give these functionalities. Cool. So what we learned yesterday was that this is just a quick recap is that so recall that using the command file and then the file name, you would know what type of file it is, for example ASCII, audio, or executable, and this is common across all the OSs that you use. In fact, a common technique for implementing or basically expressing the file types is to include the type as part of the file name, as most of you identified. For example, msword.exe. So it basically says it's a .exe file, or notes.txt file, or something .pdf file, right? So generally, in general, right, a file name is split into two parts: a name of the file and an extension, usually separated by a period character. And so what we put here is just a summary of what we learned, or in general, the file types that we talked about more formally in the last class. This is just a summary of that. So you have executable files, which usually have the extensions like .exe, .com file, .bin, or it might not even have any extension. For example, when you do GCC -o, use the -o flag, you are basically creating an executable, and you might choose not to give any extension of it. So essentially, this is a way, and then there is a source code .c, .java, batch file, .bat, .sh, text file, .text.doc, and even the word processor. All these have there's different standard file name extensions. However, what we discussed is that even in the last class, you can create your own file type. Nobody is stopping you. Uh, in fact, this docx file, right, or pptx file, this is sort of a meta file type by Windows, like on Windows, Microsoft. So, any idea what is the more basic file type, or more like so I didn't put here any pptx file type, right? If you see this, so any idea what pptx file type is, uh, or what it corresponds to in this slide? It's just a question. Just give your guess. So if I give you a pptx file, definitely that pptx is not in this usual extensions field, right? So what would it correspond to? And the hint is that multimedia. Great, yeah, getting there. Anything else? It can be a multimedia, yeah, but it is not. I mean, multimedia might be part of it. But any other guesses? Say, library, print, word processor. Any guesses? So I'm assuming all of you use PPTX, or at least have seen it. So what type of file might be? It's basically an archive file. So what you can do if you have this, say, PPTX file, or even a docx file, you can convert it, say, in PPTX, a.pptx to a.zip, and then you can extract it, and you will see there are text files and binary files and multimedia files, of course, in that archive too. So you can definitely use your own file type. That is something we talked about. So a very simple nugget is that Sometimes Unix system uses a crude magic number stored at the beginning of some files to indicate the roughly the type of the file, right? For example, whether it is for some file types only. For example, it's an executable program or a batch file or PostScript file and so on. But not all files have magic numbers. Okay, so essentially extensions. This is written here and magic numbers in Unix, which is included at the beginning of file. So whenever your program start to read that file, there might be a magic number for some file types in Unix to indicate what type of file it is. So this is what we talked about. We also talked about how file types can also be used, like this extensions can also be used for identifying or indicating the internal structure of the file. For example, if you have this object files or this like in some case when you have this object files .so files or exe files, then the operating system knows that when you try to execute it, what to do. Sometimes even if you name your .text file as exe file, for example, like you have a file called note.txt, you change it to note.txt, but operating system, your Linux or Windows, can't still execute it because the file structure is wrong. Essentially, in an ideal world, or in general, if you're not, or if someone else is not messing up with the structure and name, what happens is the extension identify the file structure. So some operating system, for example, Unix, supports a minimal file structure. For example, Unix, there's no file structure. So all files are looked at as sequence of bytes, okay? 8-bit bytes. So no interpretation of these bytes is made by the operating system. On the other hand, some other operating system might actually enforce a record structure, like it has to be a particular file extension should have only lines, only fixed length lines, or it might have variable length lines. In fact, there might be more complex structures, for example, a formatted document, or it might have a relocatable load files. So who defines these structures based on the extension? One might be the operating system. For example, Unix knows that it has to be a byte, not 2 byte, not 3 byte, one single byte. That's how I will read. That is the structure that I will see in a file. But sometimes it might be a program also. So name a program which might actually require this type of record structures, like fixed length or variable lengths. Any idea? Ah, yep, absolutely. Yes. I'm glad some of you got it. So essentially, when you use a databases, you have different databases. Like if you don't know it yet, but just look it up. I mean, it's a pretty useful tool. So you have MySQL, Postgres, and then SQLite, and then MongoDB, and X and Y and Z. All of these databases create their own file structure. Okay. Like the database, the database is essentially, yes, absolutely correct. So databases is one of the programs that require their own specialized file structures, simply because the MySQL should work just like as well as Windows, just like it should work in a Mac server and it should work in a Linux server. So it doesn't depend on the operating system. It creates its own record like file structure. Cool. So moving forward, so we know now a file should have some internal structure. It should have an extension. Okay, and we talked in detail about why is it credential. Now, with this background, let's move forward. And now what we will talk about. Essentially, what we talked so far is that there has to be a file, which is basically a logical unit of writing data to the disk. And the file should have a specific name, specific extension, specific structure even, right? Depending on the program, with some support from the operating system, like for executable files, you need support from operating systems. Now we'll talk about the access methods of these files, how to use these files in the desirable way. Now, what do we mean by using the files? Essentially, a file is just an abstract data type, right? From a programmer's point of view, we are talking about, again, file system interfaces. So if you are using file system, that actually means that file to you is just an abstract data type. Remember your C codes, right? You are basically, when you are trying to write a file or read a file, essentially you are doing some function calls. And then you will get a variable in which you can print. Use fprintf using that variable. That's all. So file is an abstract data type from a programmer's point of view. And because just an apps in general for this abstract data types, you generally have operations to make it more useful. For example, for stack, you have some operations, right? You push and pop. Simply like that, in the same idea, file also have a few operations. And in general, of operating system, like if you want to create an operating system, here is the slide essentially we finished last week. You have the 6 basic operations: creating a file, writing to a file, reading from a file, repositioning within the file, deleting a file, and truncating a file. Well, and we'll talk a little bit about why these are called these basic operations, why you need to implement them, right, in these file systems. So first, let's talk about creating a file. Okay, so creating a file is essentially 2 steps are necessary to create a file. Any idea, even logically, what are the 2 steps? Like if you, like all of you actually now coded in Pinterest, right? So if I want to create a file, even this data structure and all these things, there might be 2 steps. And what might be those steps? Very basically, remember, a file is an abstract data type, but what file does is that you need to write some data on a disk. So what might be 2 steps of creating a file? So the yeah, okay. Anyone else get a chunk of memory? Yep. Okay. Anyone else? Yep, getting there. So in general, all of you are correct. However, it is implementation specific. So in general, it is like finding space in the file system, like space in the disk, essentially, and then making an entry of the new files in the file system. Yes, what you are saying as saving a pointer, which is a C-like way of telling this, but yes, essentially that making an entry in the file system structure after finding some space for that file. Now, this creation of file is 2 steps that is done. So now you created a file, meaning that I have a pointer to write to a particular space on the disk. So for writing a file, essentially we need a system call, right? Which should specify the 2 things. It should specify where to write pointer location, and what to write, the data. And essentially remember that a write pointer, like whenever you're writing something, essentially you're writing to a file, means that you are adding more and more data to the file. So the write pointer needs to be updated. The file pointer that Ramnivas just talked about, save a pointer, or Srihash or Shubham, all of them talked about, like you must save a pointer to the file. That pointer needs to be updated when you are writing. So to read from a file, Similarly, essentially it needs only the name of the file, because for writing you need two things: the name of the file, where to write, and what to write. For reading you don't need anything. Essentially you need only the name of, you don't need the like what to write, of course, what to read, because you will only need the name of the file. So after reading, the file pointers needs to be updated. Like if you read one line or 5 bytes, then the for each pointer needs to be updated also. So essentially, this repositioning within file or seeking within file means you're not reading, you are just doing pointer manipulation. You are basically increasing the pointer within the file to read from a specific place. So why is it useful? Any idea? Why didn't you use read for seeking a pointer? Or basically, why seek is a separate command that you generally need to implement? With seek, you can go back also, of course, you're going back and forth. Yeah. Can actual, but that is not Somnath. Yes, can read whole file at a time always. Yeah, good point. But you think about it, like why do you need seek when you have read? If you're just assuming that you want to position back and forth, yes, you need seek. But can't we start reading, like going back and forth? Won't it mean to start from the file beginning, like the start of the file again, and then read up to a certain point, and then you have your file pointer in the right way? Mhm. Yes. Yep. So Srihash is getting there. So what I agree that seek should be faster by reading everything till that point. Exactly. To to be more specific, you need seek simply because seek doesn't need any read IO. You're not even reading anything. You are not doing any disk IO. You are just advancing a pointer by number of bytes. Everything computational. So seek is needed for performance reasons. You don't want to do IO. IO is slow. So you are only doing IO when it is absolutely necessary. Okay, so we have creation, writing, reading, seek. Then finally delete. Of course, you need to delete a file. So for deleting a file, you need to search the directory for the named file. And essentially, at that time, when you find that by file in the file exact uh, file by the file name, then essentially you will just remove that pointer and release that space. What does releasing that space means? Meaning that when you delete a file, others, like other files, can be written on that part. So that space is free for others to take. There is definitely something called secure delete. So this the delete in general, what works is that if I have, say, note.pdf, then I go to node.pdf, like as the operating system developer, I'll just go to node.pdf and mark that and remove that pointer to the space taken by node.pdf. That's all. Meaning that is a free space for all other programs, so they can overwrite. However, there might be this is not secure. By secure means meaning that you are not deleting whatever is in that file space. You are just saying that others can rewrite, overwrite on that space, and you are hoping that if there is a lot of overwrites by other programs, then that file will be deleted. Any idea how to securely delete so that others do not read what you deleted? So in general, you might or might not think about it, but the thing is that in general, yeah, see all the bits released, set all the bits released to null. Yes, you basically not null. Actually, even zero out the block of memory held by the file. Good guesses, good guesses. But you should know that for security, Writing all zeros might not always be good, so you write random data, not once, not twice, but 16 or even 64 times. Okay. So you take that file, you write totally wholly random data on the file multiple times so that there is no impression even on the physical disk space. And I'm not really talking about science fiction. This is truth. There are like out of the box comments to do that. And then you will delete that link to the file so that others cannot recover the content of the file, even though they get the hard disk. Okay, so deletion we talked about, secure deletion we talked about again. Now truncate. What is truncate? Essentially, you want to delete the content of the file, but want to keep the attributes. So you have this truncate where you can truncate some like truncate part of the file. If you have a 2 GB file, you'll just truncate it with 256 KB. So why do you need truncate? Because truncate can be implemented by deleting and recreating a file, right? You delete a file, and then you recreate the file. Why don't you do that? The reason is, again, I'm not going to ask this question because you already answered, or some of you already answered, but the idea is that, again, if you delete a file, you need to do the whole search the file name in the directory and then remove the pointer and everything. In truncate, you don't need to do so much disk IO, but you can just reset the, remember the file has attributes, which is the size of the file. So you reset that size. That's all you do. You reset the size to 0. All the attributes remain the same. The name remains same, everything remains same, but you reset to 0, reset to 256 KB, and that's it. That actually means that now operating system knows that after more than like aside from 256 KB from the starting file pointer, everything else is open. So truncation again. So this to actually this is important to remember that truncate, this command actually came into being simply because deleting and recreating a file is expensive, and oftentimes you might want to just play with the size of the files to remove or release some spaces. So there's, you can use truncate command, or you can use this greater than thing. Like you can basically write new data in greater than, and everything else will remain all other attributes will remain the same except for two. First, the amount of data, and second, the size. Now, as you can see, like create, write, this, all these things, it doesn't have, say, very popular functions like copying a file. Copy pasting is an art form, or necessary art form these days, right? So why is not copying a file is one of the file operations? Idea? Think about it. Why is copying file not one of the operations? So generally it means, read and write. Copy is create, read and write. Read from one, write to other. Perfect. Yes. So that means that if I give you some X other functionality and ask you that why is it not a basic functionality, then you should be able to say, like, I can just do create, read, and write. That's it. Or I can combine seek and read to actually do this functionality. Yeah, it can be used during create, read, and write. So remember this, these are 6 basic operations, because people have seen that everything that you need in file system should be available by doing this, using these functions efficiently. The efficiency is the reason you have the seek command and the truncate one. Good. So now we know the basic basic function calls. So these are file operations. Now Now, when we talked about this previous file operations and remembered them well, these are actually something that you always do in your C code or Python code or Go code or anything, right? I mean, you create the file and you read and write to it. But at the beginning, remember that you always do open file and close file. Now, how does rename work? So renaming basically means changing the file attribute, right? So essentially you'll just change in the file attribute table. You change the name of the file. You are not, or in the file attribute will change the name of the file. You don't need to read or write any of this data essentially. So yeah, so you are not really doing any operations on the file data itself, but rather you are doing operation on the file attribute. The reason is you can ideally, create a new file, so you can copy using a new name of the file, and you can actually copy the whole data in it, but it's expensive. So in general, if most of the operating system provides a way to have this rename, like where you'll just change the file name in the attribute table and update the entry. You are not going to touch the data. So even does it answer your question, Shubham, actually? Okay. So when you write code, the first thing that you do before reading or writing or doing anything like that is to open the file, and after you are done with the file, you close the file. So let's talk about open and close, which is a precursor of almost everything essentially. So essentially, when you open the file or when you run the open command as an application developer in your Python code, in your C code, Java code, C++, whatsoever, essentially you actually use this open system call. Like it typically takes a file name and a mode to open the file for reading, writing, appending, etc. So what does open call do? It basically locates the file in the file system, and it checks if the process, like your process that is asking the open call, has the privilege to access the file, and it creates an entry in your processes open file table, right? Which is a reference to the file. Like your Python code has this file open, and it uses this mode. Like what is mode? Like whether it is available for reading or writing or appending and so on. And it sets the current position within the file. Initially it's 0, like at the starting position of the file, and it returns a file descriptor. And what is a file descriptor? It's basically, think of each process. Remember the open file, like each process has this array of open files, and the file descriptor is just the index within that open file table. So any subsequent call to open files, or basically call with the files, essentially need that file descriptor. Okay. So essentially what we are talking about here, for open file, you need the open file table which tracks the open files. And that open file table increases or decreases based on your process. When it opens a new file, it will be appended to your open file table, and the index of that entry, like that open file table, the like index within the open file table where this file resides, will be sent back to you. You will use it to do more work essentially. And the file pointer is resides in the open file table, which is that pointer to last read or write location, which is per process that has the file open. So if I wrote a code to actually read a file which is reading from the beginning, and you wrote a code which already read till 100th line, then we can both read simultaneously. That means that both of us has two different pointers. Okay. It also, in general, this means the operating systems also enable file open count, which is the counter for the number of times a file is open, so that if you have, so remember the file system assignment that, or file system interface assignment that you are doing, the file system in Pin2S, what it does, essentially if 5 processes or 3 processes open a file, then the file will remain in the open file table till the last process close it. This is one problem, even even in today's operating system, sometimes you will face. You cannot delete a file simply because the operating system tells you that one process is reading that file. This file is used by someone. That's why you need the file open count. Of course, for this open call, you need the disk location of the file. Otherwise, how would you know where to point to and what to read data from or write data to? And finally, you need the access rights. For example, if I have access to read the file that Shubham has created. We'll talk about access later, but these are the main ingredients of creation of this open system call. Once you have implement this open system call, you ultimately have a pointer to the file and you know where to read that file. The close system call is simply tells the system that the file descriptor, which is basically the index, is a location which is no longer needed and can be reused. So you essentially in close system call, you will remove the pointer. That's all. Typically, the operating system uses 2 levels of internal open file tables, a per process table and a system-wide table. So far, we talked about per process table. Like when your Python code opens a file, it just adds it to the per process table, but not the system table. We haven't talked about the system table. So the per process table tracks all the files that a process has opened, and each entry in the per process table in turn points to a system-wide open file table. And the system-wide open file table, what it does, essentially it tracks all the open files in the system, which contains process independent information. For example, a location of the file is independent of the process on the disk, the access dates and file size, and so on. Once a file has been opened by one process, right, the system-wide table includes an entry for the file. So throughout operating system, there is one table, and even for per process, there is an open file table. And in open file table, like this tracks open files, which is that's what this question asks, per process or per system. So far, we talked about primarily per process, but now I'm telling you that aside from per process open file, there is also a system-wide open file table, which tracks how many files are open per system. Any questions so far from the opening and closing? Okay, so now we know file open I mean, if a file is open and then you do read, write, seek, and all these things, and then you close the file. And what is the reason for doing all this like operations, specifically read and write? Essentially for storing or reading information from the files. So files store information, and when it is used, this information must be accessed and read into computer memory so that your program or the program can or process can use it. And this information in the file can be accessed in several ways. And the simplest one is sequential access, meaning that information in the file is processed or read or write in order. one record, one line, one byte after the another. This mode of access is by far the most common. For example, like your AD text editors, right? If any text editor and compilers usually access files in this fashion, read line by line. So essentially, reads and writes make up the bulk of the operations on a file. And when you do a read in this sequential access, essentially it basically talks about something like a read next, which is reading the next portion of the file, and it basically automatically advances a file pointer in the sequential access. Similarly, the write operation is the write next, which is happens to the end of the file and advances to the end of the newly written line. Now, as shown in the figure, in sequential access, a file can be reset, the pointer can be reset at to the beginning, and on some systems, a program may be able to skip forward or backward n records. Like I want to start writing from from the 5th byte of a file. So you can also do that in some systems. So, and going at the beginning of a file, it's called rewinding. Like this is the rewind term, which actually means that you are rewinding the file and start again from the beginning, read or write, either way. But the key thing to notice, what is sequential access? You have read next or write next function. That is your primitives. Because you cannot, as Shubham was mentioning earlier, it's like if you only have read next or write next, that means that you cannot go back. So for that, you provide two more functions. One is called rewind. So you put the pointer at the beginning and then again do read next, write next, write next, write next. And you can also skip forward or backward n records for some integer n. But those are special cases in some special operating systems. So in your operating system, you can provide that functionality. It will come up with some overhead. So let's see the methods. So in the sequential access, you have read next, write next, reset or rewind. And essentially you have, you cannot really no read after the last write. So you can do rewrite. So aside from sequential access, which is read next or write next or reset this function, you can also do direct access. So think of sequential access analogically, it's a little bit like linked list. You can do just the next, 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 or before, before, before. But you cannot do random or direct access. So another method is, so when do you do direct access? Similarly, in the analogy in data structure, you can do direct access in an array. So similarly, some operating system provides a method for direct access or something called relative access. And for that, they create the file system such that a file is made up of fixed length logical records that allow programs to read or write rapidly in no particular order. So for direct access, the file is viewed as a number of sequence of blocks and records. So if your operating system actually provides some direct access API, that means the file is viewed as just an array. Okay. So for that, what do I mean array? It's basically a numbered sequence of blocks or records. So we may read block 100 and then read block 45 and then write block 103. So essentially, it's like read n, read 100, write 45, and then you position it to 46. And then even then you can do read next, which means that you read 46, and then write next, which means you write to 47. There is no restrictions on the, essentially there is no restrictions in the direct access model for the order of reading or writing in a direct access file. Any idea which ones are direct access? So I already told the sequential access is that if you take your text editor, it will be sequential access. So which one would be direct access? Often databases are often this type. So when a query considering a particular subject arrives, they compute which block contains the answer and then read that block directly. database has all these indexes to get particularly that file. That is the like database files essentially give you that capability. Now for a direct access method, you need something more in the file attributes. Essentially, you need the block number, right? So essentially, if we have read n, where n is a block number, rather than read next and write n rather than write next. So essentially, for your direct access, if you want to enable direct access, you have to also have your block number in the file attributes. But direct access is directly related to your array, and sequential access is related to your linked list. By related, I mean analogous, the operations that you can do. Now, which are the systems that allow sequential access? That is, you can only do the next, and which one gives you direct access, which can actually say you read to block n or write to block n. Essentially, some systems allow only sequential access and others allow only direct access. And some systems actually require that a file be defined as sequential or direct when it is created. So it allows both, but it has to be defined at the beginning. And such a file can only be used in the way that it is defined at the beginning. So when you create a file, in some file systems, you have to tell this sequential, it should be sequentially accessed or it should be directly accessed. What is the downside for direct access? Now you need to do all those bookkeeping, like your keeping the block number. Now remember that if the operating system, for example, I talked about databases have direct access. You can read any block. So, but if some file system essentially provides you that only sequential access or only direct access, and your program needs the other, how do you implement it? So you can simulate sequential access on direct access file. So if the file system only gives direct access, how do you sequential access? Essentially, this is your pointer. Like say you can simulate sequential access on a direct access file by simply keeping a variable CP that defines the current position, and they use the transition of function calls like this. Like when you want to do reset, what it means, you put the pointer at the beginning 0. You want to do read next, meaning read the current pointer and then advance the pointer. You do write next, you write the pointer, you advance the pointer. So this is how you can, it's pretty simple actually, that you would actually have, you can simulate direct access or sequential access with direct access file system. So any idea that if you can you simulate of course the obvious question is that can you simulate a direct access on a sequential access file? So this is this slide actually shows how you do simulate sequential access on a direct access file. Can you do the reverse? You have a sequential file system, you want to do direct access of the file blocks. Yes or no? Okay. So why will it be? So the answer is that you're correct, that it will be costly, not with the same performance. Why will it be costly? Why is simulating direct access on a sequential access file system is costly? Yep. So because you need to traverse, so yes. So essentially, if you are correct, Srihas, Dej, Shubham. So yes, so when you try to actually simulate direct access on a sequential access file, ultimately it's a sequential access. So you always have to access random parts, and accessing random parts is always time consuming, meaning that you need to go back and forth and find the right block to write to and read from. This is really time consuming. So essentially you'd have to do a lot extra IO and it will be slow. Now, there are other access methods aside from sequential or direct access, and which can be built on top of these base methods, right? And these methods generally involve the construction of the index for the file. Remember again, databases, right? So this index, like an index of a book, like your book has this indexes at the beginning, it contains pointers to the various blocks. And right, yeah, better. So and like it various blocks in a file, and to find a record in the file, we first go to the index, right? And this use this pointer to access this file directly and find the desired record. Let's take an example. So a retail, say there is a retail price database file which actually lists the universal product code, like set of records of grocery items. So it has a 10-digit product ID and 6-digit price, that is total 16 digit. If we assume each digit is 1 byte, that means each record has 16 bytes, right? And so we have 16 byte sized records. And if a disk that this retail price file is stored on, if this has 1024 bytes per block, then we can store essentially 64 records per block, because it is 1024 bytes each block. So each record is 16 bytes. So 1024 by 16, 64 records per block. And if you need have say more than like 320,000 records, 320,000 records, then in total you need 5,000 blocks. So by keeping the file sorted by product ID, we can define an index consisting on the first product ID for each block, because now you have 5,000 blocks and each block has 64 records. So what you can do, you can sort the index and put those indexes like the first index for each block in, first record for the each block in an index. Right. So this index will have 5,000 entries of 10 digits each, so 50,000 bytes. And essentially you can actually store it in the, and you can actually store it in the memory. What it means is that you have 5,000 blocks and you have sorted the product ID, 10-digit product ID. So each block has 64 records, 64 product IDs. So you can create an index which will only have the first product ID per block. And it is a small index, because 5,000 blocks, each one will have a starting product ID of 10 digit. So total 50,000 digits, 50,000 bytes, small enough to put in the memory. So essentially, whenever I want to give you a product ID and select what is the price of that product ID, you can do a binary search on this smaller index and find a particular block and do sequential access on that. So this structure allows us to search a large file doing little IO, because remember that this 5,000 this index, which is 50,000 bytes with 5,000 product IDs, that is small enough to be in the memory. No disk IO, much faster. This is assuming, of course, that you can directly access the blocks. That means a direct access method. Now, so far we talked about one file, and often your computer has thousands to 100,000 to millions of files. And we also talked about the file is created, operations of the OS implemented. We can access the files like the open close system call and creating this space in the file. So far, because although we talked about one file interface, which is important, we generally deal with operating system generally deals with millions of files in one single laptop, perhaps. So let's see how multiple files are stored and accessed from the disk using disk and directory structure. So what is a directory structure? Right. So essentially, files are stored on often random access storage devices like your hard disk, optical disk, and solid state disk like SSDs, right? And this file system resides on this disk with and consists of millions of files owned by several users. Now, what is this directory structure? This directory structure essentially organizes this hundreds to thousands or millions of files by keeping entries of all the related files. These file entries have information like your file type, location, or the mode, or all the file attributes that we talked about earlier. Now, this diagram shows a basic schematic of the directory structure. So directory is a very high level, which is just a bunch of nodes, which contains information about individual files. So these are basically your file attributes or information about individual files, and these are actual files from F1, F2, F3 to Fn. Now note that both this directory structure, which is basically indexed to access these files, and the files themselves, they reside on the disk. And this is what you know as your directory structure, like opening in this directory or opening this folder as in Windows, opening subfolders. These are basically directories and subdirectories. So these are indexes to basically a collection of nodes to read or write or access the actual data in the files. Now, a storage device, we talked about directory structure, and we'll talk about more about it. But what the directory structure resides on a disk, just like the files. And this disk or storage device can be used in its entirety for a file system. However, it can also be subdivided for more finer grained control. For example, if I buy a 512 GB hard disk, okay, 7600 or 7500 RPM or something, I don't know. And then you can actually partition this disk, right? And each partition can hold a separate file system. For example, when you install Windows or Linux, you can actually tell like I want 3 partitions. And each partition, one of the partitions have the Linux code or basically the operating system, but others are also full-fledged file system which can create where you can create directories and files and so on. So disk, in fact, some of the disk like storage devices can be collected together, something called RAID, right? RAID sets, which provides protection for failure of a single disk. What does RAID mean? Meaning that whatever, so you actually have a 512 GB disk, and very basically like your operating system divides into 256 GB, 256 GB, and you can only use the 256 GB. What happens to the rest? The rest of 56 GB generally creates a copy of your other 256 GB, so that even if one partition fails or one disk or part of the disk fail, the other will still hold a copy of the data. What does fail mean? Well, when you actually write a lot on a disk, for example, generally the sectors get damaged. Or in SSD, I don't know whether you know this, but the flash drives that you all are, perhaps some of you use, many of you use, they can only be written like 1,000 times or 10,000 times. Their limit on how much you can write on the physical device before they start losing bits. So RAID is for protecting against those failures and copying or protecting your data by making a copy. So essentially, disks are subdivided and sometimes collected into RAID sets, which are like meant for doing replication. That is a technical term. Replicate the data that you have. Now, partitions are also and disk or partition can be also used raw, that is without a file system. So some of you might actually have this, like you can format a disk. That means that you'll remove the file system, or you can actually keep it as a free space. And at least from the system level, operating system level, you can directly read or write data in it. But in general, the GUI that is given to you, you have to first create a file system, because without file system, you cannot really read or write data via the operating system themselves. So these partitions are also known as mini disks or slices, but we know them as partitions. In fact, one of the most well-known partitions is possibly, say, C drive or C volume in Windows, which host, in general, the Windows operating system. Now, any entity containing a file system is generally known as a volume, and the volume may be a subset of a device, a whole device, or it might be multiple devices together. One file system is a volume. And one single volume can also store multiple operating systems, and that actually means that many of you do dual booting, both Windows and Linux in same machine. That is possible. So essentially, each volume can store multiple operating systems. Each volume that contains a file system must also contain information about the files in the system, in the file system that it contains. And this information is kept in entries in a device directory or volume table of contents. And this device directory, or more basically this more commonly known as the directory, records information like name, location, size, and type for all files in the volume. So what is a volume? One file system, whatever it resides, it can be a volume. It might be multiple hard disks even. It might be networked, but one file system. And that file system essentially contains the device directory or volume table of contents, which basically means this whole directory, subdirectory structure that you see, this is in one single file system, meaning in a single volume. Aside from these general purpose file systems where there are this volume, there is one file system, multiple files in the file system, there are many special purpose file systems too, which is frequently all within the same file system or computer. This is special purpose file system is often very useful when you're doing embedded systems or special device programming. So what is a typical file system organization? This is here we'll stop. So this is summary of what we learned today about this typical file system organization. Each file system has a directory, and under directory, it is basically there are multiple files in this file system, and the directory to actually contain the index of these files. You see there is one disk 1, it has two file systems, partition A, partition B. Each of the file system had its own directory structure and its own files. What is directory? Just pointers to files. This directory structure is hierarchical. You have directories and subdirectories and everything, but it's nothing but just the index to the files. Similarly, there might be volume or partition which spans multiple devices, like in disk 2 and disk 3 has one file system, which is called partition C. This one file system have two disks, have multiple files, and have one directory. So one file system has one directory, and it's called a volume. A volume can be, there might be multiple volumes within the same disk, like here, disk 1, 2 volumes, or same volume or same partition, same file system in multiple disks, like here. Okay. So we'll stop here for today, and we'll continue about the directory structures on tomorrow's class. Any questions? Any questions? If not, yeah, feel free to ask any. If you have any questions, or feel free to leave. We'll continue from here tomorrow.